Welcome back. This is another three-phase power problem. It's a word problem. So I've written out all these words here. So given the magnitude of the line voltage at the terminals of a balanced three-phase Y-connected load is 660 volts. The load impedance is 30.48 plus J 28.86 ohms per phase. The load is fed from a line with impedance of 0.25 plus J2 ohms per phase. And they want you to find the magnitude of the line current and the magnitude of the voltage at the terminals of the generator. So they're talking about terminals, right? The terminals of the load and the terminals of the generator. So there's stuff hidden. So let's draw the whole diagram here. So we've got a three-phase Y-connected load and a generator. So the generator is modeled by three voltage sources, okay, at little terminal N, which is grounded. So that's a terminal, right? The neutral, which is a ground, is a terminal. And then there's an internal impedance going out to a terminal A, and then there's an internal impedance and terminal B, and then another one, and then C. So there's four like bolts on this generator. If you imagine this big old piece of equipment, there would be three power terminals and a ground, right, that you hook up cables to. So that's what they're talking about at the terminal. So this internal impedance is inside. We don't see it directly. We're just that's what we're trying to find, is the voltage at this across these two terminals. Actually, the line voltage. They want should write that out. The line voltage. So this is V sub L, all right, and that's line to line. When they say line voltage, they mean line to line. So either AB or AC or BC. Let's just choose one. Let's use this one. So this is V little a little b, plus and minus, which is kind of arbitrary, the way we put the plus and the minus. All right, then let's get this thing drawn. There's a Z sub L and another Z sub L. It's balanced, so these Z's are all the same. And this is some load. It could be a giant motor or something, and it has terminals, like, right? If this was a generator, it would have three power terminals and a neutral, which is typically grounded, and then you have a motor, say that it's driving a very big industrial motor, and it has three terminals. Or if this was an electric car, you could, could be, some of them use three-phase motors. So anyway, this thing's connected such like that. Oh, there's impedances in here too, I left out. So there's line impedances, and we'll use a little L for those guys. Okay, there's three line impedances, Z sub L, Z sub L, and Z sub L, which is given by this 0.25 J2 ohms per phase. There's three of them. And then there's this load impedance, 30, 48, 27, 82. There's three of these guys. And let's see, the magnitude of the line voltage at the terminals of a balanced three-phase. So they're asking for line voltage at the terminals of the load. They're telling you this right here is V sub line. This is 660. Actually, specifically, this is VAB. They're telling you that V sub L is 660. Because remember, there's three of these line-to-line voltages, and they all have the same magnitude, and they're just giving you one of them. So for our picture here, let's choose VAB. And let's make VAB our reference. Okay, so since they're not giving an angle on here, we'll just choose this as a reference. So it's a phasor now. And then they're going to want us to solve for this thing. They're asking us to find the magnitude of the line voltage at the terminals of the generator. That's line to line. Line voltage means line to line, and they're talking to the terminals of the generator. So we'll choose these terminals here. And they want the magnitude of the line current. So since we're dealing with AB, and we could do this one, but let's stick with A's and let's solve for that, and then they're just asking for the magnitude, but we'll get the phasor IA and then just pull out the magnitude. So so part A, the magnitude of the line current, which by the way is I phi. Yeah, so we could get it from IA just by taking the magnitude if we had IA, and we could get IA if we had V sub AN. So we're given this magnitude of the line to line voltage, and then we're just choosing 0 as the reference. But then we could calculate VAN from that, because we know that this thing is √3 smaller with a 30-degree shift. So and then we could use Ohm's law. So basically, VAN is VAB over √3 minus 30 degrees. So it's this one's 0, so it's going to be 660 over √3 with an angle of minus 30 degrees. So it's 381 with an angle of minus 30 degrees volts. So that's VAN. It's just √3 smaller and 30 degrees off. I'm just saying off because I don't want to misspeak on lagging leading. But look at the diagram of all of those crazy things. Look at that thing. Look at that. So IA falls out by Ohm's law, all right? So I sub A is going to be V sub A N, because through here, just use the current traveling through this load, because we're given the load impedance. So V sub AN over the impedance of the load, it's going to be 381.05. I guess I got some more points on there. Angle minus 30 over 30.48 plus J 27.86. This is going to be 10 with minus 66.87 degrees amps. So I phase is just the magnitude of I sub A. So it's just 10 amps. And that's the first answer, right? So it was all about just understanding the words here and figuring out what all those things are on the three-phase equivalent circuit. And then once you have that down, you can realize that you can go right in here and get I sub A. So we got I sub A. So so that was part A. So part B. So part B, they're asking for the magnitude of the line voltage at the terminals of the generator. So they say line voltage, they mean line to line. So since we did VAB over here, we'll do V little ab over here. And just to mix it up, we could use KVL at any loop we could go inside this loop here, which we've done before. But just to mix this up, we can go around the outside loop just to make it a little bit, different. So, so the way, and fun stuff happens here. So, first of all, there's 3 phase currents, and there's a convention on drawing these things. We draw them all. We draw them all that way, going from the source to the load. So the arrow's going that way. Now, it gets a little confusing because we've done this with DC circuits, and when we choose all positive directions like that, we know that one of them will have a negative value, and that will happen here. At least one of these guys must have a negative value. That's true. Now, it's also true that these are AC signals and they're wiggling around. They're going from positive to negative. But that's true, but it's not particularly helpful to think about it that way. So sort of treat it kind of like it's DC, kind of. The phasor values here will take care of that oscillation thing for you. You don't have to think about it too much. So how do we write this KVL around the outside loop? How would we even write that? So I'm sort of choosing this positive polarity at the top here. That's a little bit, well, it comes from the AB sequence here. Okay, although it may seem a little bit arbitrary. Okay, now, so I'm gonna write this as source equals loads. So I'm assuming that this VAB source is dropped across what? The ZL load, then it's dropped across VAB, which we know, and then it's dropped across this other ZL load. Right? There's a drop here, which would be ZL and IA. I mean, there's a drop here, which would be ZL and IC. I'm mixing up C's and B's here. Shoot. This is B. This is C. Yeah. So there would be a drop here and a drop here, but by Ohm's law, there would be ZLIA and then ZLIB. But those are wrapped up together in the total voltage drop. So we'll use Ohm's law here, and then we'll use this VAB here, and then we'll use Ohm's law here. But now here's where it gets freaky. So there's a plus and a minus because that's the direction of our voltage drop. But given this arrow here, there would be a plus and a plus and a minus. But we're summing drops, so it ends up being. Here, let me write this out in. It ends up being V. You could write it this voltage drop across here. You could write it as V little aa, which works out to be IA Z sub line. Okay, plus VAB plus V big BB, and okay, then we need a minus sign. Right, for this term, this V big B to little b, because of our convention of drawing the current arrow this way and this polarity going this way, but we're going backwards, so we need to throw in a negative sign. So this would be negative I B Z subline. Okay, so that's because of our, it's to to fix our, polarity convention. Not really sure how to say that, although we've seen things like that previously, but there's that. Okay, then let's see. Now it's just punch plugging in the math. Need a little more room. So VAB is going to be IA, which is this thing, 10 angle minus 66.87 times our line impedance, which is Z25 plus J2. That's this first term, plus this guy here, which was 660 angle 0, plus this, okay, minus IB, which is so we need IB. So I where is it? So IA is let's see, let's draw it down here. So 66 degrees. So this is IA is 10 angle minus 66. So this is minus 66 degrees, and then IC and IB are 60 degrees apart. So basically, so this is another 120 over here. So what we're saying is IB is it's IA minus 120. So it's a 10 angle minus 186.87. Okay. And that's what goes here. So this is 10 angle minus 186.87 times the same line impedance, 0.25 plus, I'm running out of room, J2. Just barely squeeze it in there. Okay. So there's this funny weirdness with this negative sign, which is, I admit, is confusing, but watch out for that. And the other weirdness is that we need this IB in here, and that comes from the understanding that these guys are 120 degrees apart, and it should be 120. I didn't draw it super good, but all three of these are 120. Same magnitude, just 120 degrees apart. Anyway, if you crunch this thing out, the answer comes out. Some of these are in polar and some of these are in rectangular, and make sure you're entering that in your calculator right. But anyway, you get 684.7 angle 2.10 degree 10 degrees in volts. That's VAB. They're asking for, what are they asking for here? They're asking for the magnitude of the line voltage at the terminals of the generator. They're asking for the magnitude of this, which I'm calling VL. Seems like it needs another. That's fine. And so VL is it's just 684. That's the answer. Just the magnitude of the vector, or phasor, sorry. Yeah. So that's not too hard, just this negative sign and then this conversion or calculation of the other current. Then we got the √3 thing in there. Not too difficult. But anyway, the hardest part about these word problems is just realizing what they're talking about, so you know how to approach it. All right, thanks.